I'm a senior software engineer at Amazon. I'm a committer for Apache Airflow. I'm working on Airflow for about 4.5 years now, I think, maybe since June 2021. I've been at Amazon for 8 years. I started on the marketplace side of Amazon, but then helped build and launch the MWAA service, which some of you might be familiar with. I helped build in GA and support that, and then started a open source team at Amazon. So we work basically full-time on Airflow itself, which is pretty cool. I spend most of my time on executors for no reason other than I kind of just fell into that space. I worked on the AIP51, which is executor decoupling, making a nice interface between executors and the scheduler. Helped build a couple AWS executors, ECS and batch, and then worked on AIP61, which is multiple executor configuration, so running multiple executors concurrently. And now this year, another executor topic. So we need to cover some fundamentals of executors. I promise I'll go through this quickly. This will be revision for a lot of people, but it's important for later in the talk. So first off, executors do the where and how. The scheduler says when a task should run, and the executor says where that should be run and how it should be run. The scheduler regularly heartbeats the executor. The executor is just an in-memory piece of code running in the scheduler. It's not its own process in Airflow. They communicate over that well-defined interface I was talking about earlier. They're pluggable, extensible. You can write your own. Please do. And if you do write a cool one, let me know. There are many types of executors. First and foremost, the local executor. A lot of you will know that one. It's good for development. It's kind of easy to use. It's just built in. You don't need to do a bunch of setup or manage a bunch of clusters. It's very fast. It runs just right on the machine. You're not communicating over a network or spinning up some hosts. But it's very difficult to scale, and it shares resources with the scheduler. So you get those conflicts, which is not great. And then you have remote batched executors. This is kind of like Celery Executor is the main example there, but also the batch AWS Executor. So the workers are now decoupled from the scheduler, which is good. And often you can have big, beefy hosts on that queue. So the executor is sending tasks to some queue in Celery, for example, and then workers are pulling those. Those workers can run multiple tasks, so you get nice parallelism and usage of your hosts. It's pretty low latency, especially if you have workers hanging around present waiting to take tasks. But some of the cons are, if you do have those idle workers waiting to take tasks, it's a little expensive. You have to pay for those hosts. Auto-scaling tends to be kind of slow, depending how you're managing the hosts that are backing Celery. And the environments, especially if you're bin packing those tasks together, are not task specific. And you can get a bit of a noisy neighbor problem if you're running multiple on the same host. And then the last big category is remote containerized. So Kubernetes Executor is the kind of the nominal example here. So each Airflow task runs right inside its own pod or container. So no noisy neighbor. You can customize that environment exactly how you want it. Resources, system libraries. The workers are only alive for the duration of the task, which is kind of nice, so it's cost effective in that way. But the biggest con is the latency on startup. You have to launch a pod or start a container, and that can take some time. And if you have just a task that's doing some set it and forget it or some API call that only needs to run for like a few tens of milliseconds, it's kind of expensive to set up a whole pod just to run that. And then you're managing something like a Kubernetes environment. So here is kind of a graph of those two things. There's many ways to measure executors. I've picked a couple here just to illustrate my point. So on the y-axis we have speed and convenience. On the x we have isolation and scalability. So you can see the local executor is really high on speed and convenience. Just super easy to use. It runs really fast, but it's terrible isolation and not very scalable. And then you just have something like Celery and batch. So they're a little slower, but we're getting better on isolation and scalability. We have those dedicated workers, but those workers may be running multiple tasks. And then we have Kubernetes and ECS Executor here. So we're getting farther to the right on isolation. They're much better at that. They're pretty scalable, not the most scalable. And then you're getting a little lower on the speed because you have to spend the time starting up those containers and those pods. And this is really just to illustrate the point that like this would be amazing, right? Something in the top right quadrant. I want it to be really fast. I want it to be convenient. I want it to be isolated and scale like heck. You've all seen the title of this talk, so you know exactly what's coming, but it's the Lambda Executor. So here's just some quick hits about Lambda. I'm sure all of you know Lambda, but it's ephemeral and containerized. They're running on Firecracker VMs, which is an AWS project, open source. They're massively scalable. We're talking like hundreds to thousands of executions per minute, thousands of concurrent executions, very low startup latency, especially if you're dealing with like warm pools or you have provision currency. They're highly available, retries, dead letter queues, super resilient. They're ideal for short to medium tasks, as you do have the infamous 15-minute max execution time, and you're restricted on your memory and CPU and storage. You're not going to be running huge compute workloads with hundreds of gigs of memory or something. You're limited to about 10. This is a simplified diagram of how it works. Watch the numbers here. It's going to move around the diagram to tell you where we're talking about. So the Lambda executor, like any other executor, receives its tasks from the scheduler. It's going to queue them internally, and then it's going to make asynchronous invoke calls to Lambda. And it needs to be asynchronous because we don't want to block the executor thread. And then we move on to, Lambda's going to run your task. It's up to the user to configure the function, whether that's setting up the Docker container that backs it and the app.py handler code. We have some documentation here. I'll link it to the end, don't worry. Where we have examples on the Docker files and the app handler. I would really encourage you to use our example app handler. You'll see why in a second, but it's very easy to pick up and customize. I don't think many people will even have to touch it, but keep that in mind. Okay, and then your Airflow task is going to run, whether it passes or fails. The app handler is responsible for sending a message to an SQS queue. And this is where it differentiates a little between most executors, which is there's no convenient way to describe a currently running Lambda invocation, especially if it's asynchronous. So we can't say, what was your result? How long have you been running for? So it's up for the Lambda handler itself to report back to this results queue. And again, this queue is something that you provision and put in your Airflow configuration. You're basically giving us the ARN of your Lambda and a couple of queues. And the messages that are sent to that queue need to be in a particular schema, in a particular format, which is again why I really encourage using the app.py we provide. And then if your Lambda fails, like catastrophically, your code ooms or there's some uncaught exception, or God forbid, like an AZ goes down in Amazon, Lambda will do some retries, and if it can't successfully retry, it's going to send a message to the dead letter queue. This is going to let us detect when those tasks have failed catastrophically. And then the Lambda executor reads from both those queues. Basically, it's starting invocations with a particular key and then waiting to see messages in those queues with that particular key with the payload that tells you the result of that task. And then after that, it's normal executor stuff. It's going to communicate with the scheduler over that interface that they share. So here's an example of a hello world task. Sorry, this is Airflow 2.10. I know we should all be about 3.0 here, but I wrote this code a while ago, so all my examples and screenshots are from back then. And this is the setup I had that I could resuscitate from that time. But we're running you're running just a simple task. It says hello world. It just literally prints hello world. That's why I don't even bother showing you the code. So all of the runtime you see is basically the machinery of Airflow starting up, tearing down. So everything else is just measuring the time of the executor and the task running. So you can see that the local executor is on the top here, and it stays queued for about 3 seconds. And you can see the Lambda executor on the bottom, which is queued for like ones of milliseconds longer. And then if you look at the runtime is about 2 seconds for local, and Lambda is again maybe like a few hundred milliseconds slower, maybe 500, 700 at most. This is pretty remarkable. The local executor is running on that host, no network, it's not spinning up any containers, it's not sending any results back, and the Lambda executor is going to your VPC, it's starting up a Firecracker VM, it's running your code, it's sending that SQS message back. This is a pretty remarkable runtime for something that's not running locally. And to show you more data of just how fast these things are, there's a lot of numbers and names here, don't worry about it, but at Amazon we run system tests for each of our operators. So basically we have DAGs for each service, whether it be batch or Bedrock, and we exercise all of the operators that service has in Airflow in one DAG end-to-end. So that's like create some environment, use it, tear it down. And this just gives us a nice data set to work with that I have access to. And we run it many times a day with different executors. And I want you to pay attention to this column here. Here we're comparing the ECS executor, which is one of those containerized executors where the tasks are going to start up in their own container each time, and then compare that to Lambda on the right. We're talking like 3, 4, or 5 times faster in some cases. And this is a comparison with the batch executor. Batch is a little bit faster, but still 2, 3x faster. Lambda is still 2 or 3x faster than batch even. This is a Apple-esque graph of that data. So on the y-axis we have minutes of runtime of those entire DAGs, and on the x-axis we just have those exact same data points. It's those system tests, that same 10 we were looking at. And this is just a graphical way to view how much faster Lambda is. Lambda is this orange line here, and then ECS is this light blue, and batch is the dark blue here. But what's interesting is that if you organize the system tests, not just randomly or I guess alphabetically, but by number of tasks in the DAG. So here on the left we have a low number of tasks. The lowest we have is about 5 in that data set of the top 10 I took. And then the highest is just over 20. You can see that if the number of tasks is low, the difference isn't huge. It's still big. But as the number of tasks increases, the difference between them starts to increase. Because again, you're paying that penalty every time you start up a task with a containerized executor. you're paying the time it takes to start up that pod and tear it down before you can move on to the next task. And if you plot a trend on those, you can really see the difference. Lambda is almost flat. You can just keep chugging tasks at that thing, and it's going to just run just about the same as if it had few tasks. And then a lot of you are going to say, but what about that 15-minute timeout? How can I run anything in less than 15 minutes? Of that data set that I have easy access to, all of those operators that we test for AWS in our AWS package, which doesn't include all of them, but it's most, all of them but one run successfully in the Lambda Executor. It's EC2 hibernation, if you're curious what the one is. Turns out it takes a long time to hibernate an EC2 host from time to time. And this is going to differ on your execution pattern. So our system tests execute the absolute base case. So if you have some big like EMR job you're doing, if your job takes a long time and you're not waiting in a deferrable or asynchronous way, then yeah, you're going to breach that 15 minutes. But most of these operators in their basic case can be used on this. And if you're using deferrable operators, then this is really your friend, because this is going to kick off that action really quickly, which is kind of the perfect use case for Lambda. Start something quick and then tear down, and then the trigger is going to wait for that task to finish and then resume on another Lambda invocation. So I hope I've convinced you that Lambda's pretty good. And it's not the only one. Lambda is generically known as a function as a service application. So I think that if you say it fast, it kind of sounds like fast. So I'm going to try and make fast executors a thing as a new executor type. So we have local, that sort of batch, container, and then containerized, and then fast. They're distinctly different. They all have this like async execution pattern. They manage their own internal queuing. They're all super fast, super resilient, scalable. They all have these in-memory or memory and disk restrictions. GCP, Azure, IBM, they all have fast applications. It's going to differ on which service you're using and which tier of which service, of course, and they're all generally time limited as well. Again, we'll differentiate between which service you're using and which tier, but they all fit this general profile.